Okay, it's already 4, but we will wait for a few minutes and then we can start. If anybody joins, let me wait. Okay, okay, so anybody, no, nobody joins till now, so we can start discussing. If eventually anyone joins, then he can follow, or no, otherwise we have option that I will upload this lecture or all lecture eventually I uploaded in YouTube, and that link, YouTube link, I have shared through the spreadsheet. So you can have the lecture from YouTube as well. So okay, it's already 5 minutes, so we can start now discussing. Today we'll discuss basically canonical ensemble as we have planned. So today we'll discuss canonical ensemble. So okay, before that I have to share my screen, right? So let me share my screen. Yeah. Okay, I hope it is visible. I don't know, nobody is there, so I have to be optimistic that it is okay. And now we'll start. So today, let me start with our topic is today we will discuss about canonical ensemble in detail. Great. So we have discussed that what is ensemble and various types of ensemble like canonical ensemble, microcanonical ensemble, grand canonical ensemble. These things we have discussed, and how this ensemble idea James gives this idea um, that we have discussed, why it is groundbreaking, and you can think like that this is the main breakthrough uh, in last 100 years in statistical mechanics, because in the concept of time average it's okay, but you can't solve You can't calculate, you can't estimate the average values or any other properties by using the time average. That is not possible. So that's why Gibbs came with this idea, which is ensemble idea. And using ensemble idea, you can calculate the ensemble average. Now there are various type of ensemble that we have discussed. If we consider that macroscopic system is a is isolated system, then in ensemble, what the basic idea was that in ensemble we have to make infinite number of copies, right, of that macro state, so that each and every copy will represent various type of microstate. And due to huge number of copies, that various number of microstate essentially will be equivalent to the all microstate which would be generated if we consider the time average. That's the main concept, right? So here also that if the system that is the isolated system, then what will happen in case of isolated system, it is not interacting with the surroundings. So in case of isolated system, uh, ensemble you make from isolated system, that is called the microcanonical ensemble. And as it is a isolated system, so eventually nothing will change. N will be constant, V will be constant, U will be constant for each and every system, each and every macro state, this will be constant. But the problem is, not problem is, it's okay, everything will be constant. So from there you basically you don't have any distribution because everything will be constant. But what will be the factor, the microstate will be different for each and every cases, and you can have a delta function like distribution from a microcanonical ensemble. Now coming to the canonical ensemble, if your replicas macrostate that are basically not uh, isolated system, it's a closed system. Closed system means it can exchange energy with the surrounding but not the particle. So it can only exchange the energy. So in that case, you will make the copies of that closed system, that will be canonical ensemble. Now, as the energy can be exchanged, so obviously energy will not be fixed. So for different macro state, the energy will be different. But we have kept in a reservoir, which is a thermal reservoir. Means you can think like our environment is in. Okay, anyway, I think. Okay, I was discussing about this canonical ensemble. I started actually. Sorry, I was late. Oh, it's okay. Just I started, I have not written anything. I was just saying about the ensemble, recapitulating the things that you know. Actually. Oh, okay. So let me connect it again. Okay. So you know that canonical ensemble is actually the collection of closed system. So you have to make the infinite number of collection of the closed system. Across it will be same, but each and every copy, each and every uh, replica will essentially represent a different microstate. Okay. And as you are making infinite number of copies, you will have all kind of microstate possible, which you can essentially get from the time average as well. That was a canonical, and for grand canonical, you know that system will be open system. Okay, so first let me draw the canonical ensemble. I have drawn it before, but still let me draw it again. My screen is visible, right? Yes. Okay. Screen is visible, but my headphone is not connected. Now I can figure out it. Oh shit. It's pathetic. It's a new headphone, but still I don't know why. Probably it's problem of my laptop, not the headphone. Mm. Voice is clear, but I have put my headphone in my ears, but I can't hear it. I can hear the sound from my laptop. So what's the motive to put in the headphone in ears then? What? Say something?
What?
Now it's connected. Okay, if my voice breaks down or if there is any issue, then please uh, notify me. Okay, so this is our infinite number of copies we have made from this. This is actual macro state. Okay, this is actual macro state, and these are all copies. We have made infinite number of copies of this actual macro state. Each and every copy is a same macro state. Macro state is not different. Macro state is same, but all are the different micro state. It should be some may be equal, but essentially this micro state is different. Why? Because you are taking different orientation, different pattern. Everything will be different. So let's say these are the different. Like this is a macro state. This is another macro state, and this way. Now these systems are basically closed system. So these system are closed system. Macrostate is closed. So it can exchange energy, but it can't exchange the particle, right? So when you take this infinite number of copies, it will essentially exchange energy. Is it okay?
Yes.
So there will be exchange of energy. So when there will be a exchange of an energy, then what will happen? The energy will be different for uh, all. Okay. And now but we have kept this entire system in a thermal reservoir like that. This is a thermal reservoir which is in uh, temperature T. It's in equilibrium. So it's in equilibrium means let's say your an example of thermal reservoir is our environment. Let's say temperature is 30 degree. So it's a thermal reservoir of temperature 30 degree. So when you are in contact with the reservoir, your temperature will be also 30 degree. Or let's say you have kept a box in nature, and then it will be at equilibrium, the temperature will be 30 degree, right? So kind of we have kept all macro state in equilibrium with this external heat reservoir, which is at temperature 30. But essentially, the NV will be same for all reservoirs because all sorry, not reservoir, all systems. But energy will be different because energy can be exchanged. So let's say this energy is E1, this is E2, and so on, E3 something. So constant thing is what? NVT is constant for all. So that's why our canonical ensemble NVT is constant. If we
Average is also constant.
average we will calculate. Okay, average will be constant. Why? Because that is average. Already you will average from all systems. So it will be a fixed number, no? It will be a number. These are different.
The energy is changing between all the ensembles.
All the copies.
Yes, all the copies, the energy is changing.
For this copy, let's say it is E1, for it is E2, it is E10, it is again D1, it is again E2, something like E5, E6, like that.
Is it possible to two have the same energies?
Obviously, that will account. We'll do general calculation today. Don't worry. Because it's not 20 or 30, it's infinite. Okay. So
We can
showing
calculate the number also.
uh, number of what?
How many are in the energy E1? How many are in
Ah,
T2?
Not calculate, we'll assume that. Okay, so this is clear, right? This canonical answer is clear. Now we'll do totally mathematics. So this physical picture should be clear first. So I think
Yes,
that is clear.
yes,
Okay. So now we'll do the entire mathematics. So it might feel quite rigorous, but it's not very difficult. Okay, I will try to explain it. Okay, just be patient and we will see that we'll derive the our partition functions average. So it will be a long derivation, but okay, let me start. So let me start with some postulate. If you remember, in case any derivation, we start with some like postulate kind of thing for kinetic energy of gases or any other derivation. For quantum mechanics also, there is some postulate. So here also, we will start with some postulate like this.
yes.
Okay. So first one is temperature of each copy is same that you know, and which is T. Energy of each member. Member means copy is different. May be different.
Can temperature be exchanged between two copies?
Temperature can be exchanged. Temperature is a quantity to be exchanged.
NVT is constant for the macroscopic thing, but for the microscopic, it can be changed.
No, you have kept this all macro state in equilibrium with a external heat bath. All macro state is an equilibrium with the external heat bath T. So all temperature should be T. Let's say
Yes,
you have 10 boxes, all kept in sun, let's say. So sometime it will be equilibrated with the outside temperature. So if outside
yes,
temperature is 50 degree, all boxes should be at 30 degree. Nah?
yes,
That's the zeroth law of thermodynamics. So obviously, the temperature of all copies will be same. Correct? That's the case.
yes,
That I have answered yesterday. That how then energy can be exchanged? Let's say all temperature is same, then how the energy can be exchanged like that, right? So temperature is essentially signifying the kinetic energy. There are many other modes of energy. So that energy can easily
yes.
be
Many other modes.
that can be okay. So may be different. Okay. Third one. So what will be the energy values? Energy eigenvalue, whatever you want to say. Uh, means we'll assume that here, I'm giving example. For first copy, the energy is E1, E1 NV. You can write it for first copy. For second copy, let's say it is E2 NV, okay, and so on. Why NV? Because if your NV are different, then energy will be automatically different. Nah, we are not changing NV, but let's say your macro state is now different. You have taken another ensemble of a different NV macro state. So obviously the energy should be changed. You get it?
Please explain it.
Let me again explain. You see, you can see the ensemble, right?
Yes,
This is the ensemble of what? This is ensemble of this macro state.
yes.
This macro state has n number of particles v amount of volume, right? Now you have another macro state which has n1 number of particles v1 volume, and you have made the same ensemble keeping the same temperature T. Then the energy will be same or different.
Same
Energy will be same. How?
for
Energy?
same N and V.
No, 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 no. For here, for no, no. Your N here different. I'm saying this
Then
ensemble
energy will be different.
for this ensemble NV is same. Correct? You have another ensemble which has a different NV. Let's say that is N1 V1. Then
Then
their
energy will be E1.
then yes, then their energy distribution and their energy distribution will not be same, right? That I am
Yes.
saying. That will be different. So that's why this energy I am choosing, this is essentially a function of NV. But for a fixed canonical ensemble, we are not changing NV. If you choose another different canonical ensemble for different macro state, then obviously this NV will be different. This is the catch. Okay?
Okay.
Okay. This is our energies, and we have assumed that when we will write the energy, let's say A plus 1, this is a energy state, some energy state. These are all energy states. It essentially means it's greater than EJ. Okay. Okay. Energy of T, let's say E3 is greater than E2. We generally do that. That's why I have written. Now,
By changing N and V, the energy is different. But for same N and V, how energy can be different?
that we have already discussed. For these canonical ensemble, N and B is same, temperature is same. So the energy can be exchanged between these copies.
Yes.
That's why energy will be different. Okay. Temperature is same, but you are making copies which can exchange energy among each other.
I am taking energy as a function of N and V.
No, 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 not only N and V. That I am saying. This
Okay.
E1 is now function of N and V. E1 means let's say some copy number one, assume. That is now N and V. Already you have exchanged the energies. After exchanging, I'm saying, don't confuse it. Just think like that. You had this ensemble, and after exchanging energy, the energies are E1, E2, E3, and so on. Correct? Now you have a
Yes.
different ensemble with different NV. In that ensemble, after exchanging energy, this energy should not be E1, right?
Yes. It should be different.
It will be different. That I am saying. Distribution will be different. Obviously, in this ensemble, energies are different. E1, E2, E3 will have, but another distribution also where N and V are different, then also the energy will be different, right?
Yes.
Okay, that's what I'm saying. Okay, so this is J plus 1 and J. Now we are assuming for jth energy level, the degeneracy is Gj, which is function of this is the degeneracy of Ej. This means that what you are saying means that there are Gj number of energy level having energy Ej. Okay,
All energy level has degeneracy.
may or may not. If G1, that means no degeneracy is there. Something. Okay, this is the degeneracy of Ej energy level. That's why okay, it's better to this. Maybe equal, na? Now I am taking the
Yes.
example. It will be clear. Just see. So already we have the state numbers. The copy number. This is the copy number. This is one, two, three. Some copy is L and goes up to infinity. Or let me write it like these are copy numbers. Correct? Now
Yes.
you have the energies. Energy are, let's say, you are starting from E1, E2, E3. Okay. So like this, there are these energies minus one and so on. One thing you don't confuse that there are, let's say, 10 copies. Okay. Let's say I'm saying just 10 copies. So how many states can be possible?
10.
It may be less than 10 as well.
Yes, but cannot greater than 10.
And not greater than 10, correct? So that is the upper limit. So that upper limit is I'm writing that is called A. This A is number of things, capital A. It essentially goes tends to infinity.
Yes.
Okay. But we will represent it by now. That's it. And one thing, this let's say you the state one means having energy one. This would not be the. It's not necessary. This is the first copy of the ensemble. Okay, this is clear. I am
Yes.
saying there are let's say 10 state and there are four levels: E1, E2, E3, E4. Four energies. I'm just drawing it. Just you. Let's say you have nine levels. But there are four kind of energy. This energy is E4, this is E1, this is E1, this is E3, this is E2, E2, E4, E4, 4. It may be correct.
Yes.
So there will be four state. First state is, or let's say state 1, having energy E1. Second state is E2, having energy E2, then E3, and then E4. Okay, is it possible?
Yes.
That's what I'm saying. So one thing you have to remember that state number may be equals to capital A, which capital A is here 9, but state is 4. So that is not the always true. It may be less than 8, generally less than 8. Because you have here now, what is the population of 1? Population of 1 means this population is not the actual population of molecule. This thing you should not think. We are not inside a macro state. You have to remind it's not in molecular level. This is the energy of each and every, this is the energy distribution of this macro space in this ensemble. Means, so how many macro states are there with having energy one?
Macro states or micro states?
All are the macro state, na? Same macro state, but different micro state. So you can say different micro state. So how many micro states are there with having energy one?
Two.
Two. So you can't draw like two. This is not true because
Why?
it's not, you can't draw it here two. Get it? In generally, what we do, we have energy V1 with two micro, just draw two. It is not true because true. That is not true because here this is not the molecules with having energy U1, correct? So you can draw it like
Yes, yes.
two microstate with having energy U1. There are only again two microstate with energy U2, one microstate with energy E3, and other four microstate with
Three
energy.
micro state and four.
So this should be the so that's I am writing here. Okay. So now the distribution. This distribution, let's say A1 number of microstates are there with energy E1. A2 number of microstates are there with energy E2. AL number of microstates are there with energy EL and so on. Clear? And this distribution we generally write distribution this distribution of AJ. This is a set of A. Correct? A means the distribution, so that's why it's set of AJ. Is it clear?
Yes,
Okay. So just now check whether we can write it or not. Okay.
yes.
This A1, A2, A3, you don't know how long it runs, but it's sum over all ages. This should be the total number of copies. Okay. And
If one is more than number one,
what's the, what the number one means?
two E1 or five E2.
How to E1 and 5 E2. E1 is the number of copies with energy E1, A1. So how it can be 2A1?
In the upper picture, E1 has energy has of two microstates.
That is A na. A1 has energy 2 microstate. That means A1 is 2.
Yes, so the summation should be AJ EJ.
AJ is then that is the energy.
Yes,
It is not energy. You are assuming this is calculating total number of microstate.
yes.
So how you can calculate? For here, it has two, it has two, it has one, and it has four.
Summation
So,
over all things.
this will be A1 plus A2 plus A3 plus A4. So A1 is 2, A2 is 2, A3 is 1, A4 is 4. Then it is 9.
Total nine.
So that's I'm doing. Same thing.
Yes,
A1 can't be repeat here because this is the count of repetition. So how can I can repeat? And so on. Okay. Is it clear?
yes,
If, if there is any again doubt, you should ask because these things are very crucial. Now we are defining. So there are A1 number of levels, A1 number of not levels, microstate with energy one, right? So what will be the total
yes,
energy of that state? That is A1 E1.
Yes.
Just here two microstates are there with having energy E1, so total energy is E1. Here total energy is 2 E2. Here total energy
E3
is
and 4 E1.
4 E4.
Yes, 4 E4.
So it is A1, E1, A2, A2, and so on. So total energy will be
Sum of
AJ,
her AI is EJ.
AJ. This is the total energy of the all microstates. Clear?
Yes.
Uh, this is not the average energy of the macrostate. That is not true. This is the total energy of the all microstates. Okay. Now, now just understand this was our distribution, right? This is our distribution. These things. Correct?
Yes.
Just keep this example in mind always. Then it will be easier. So what is here distribution? Distribution is here 2, 2, 1, 4. This is the distribution.
Yes.
Now energy is following being exchanged, correct? In the system that is,
Yes.
yes, it may possible you can have other distribution as well. You are just calculating, right?
Yes.
So first time you make some ensemble and you will have this distribution, ensemble of this nine state, and you see this distribution is there. Okay. Some other guy make the same ensemble. Same ensemble means ensemble with same macro state with again nine system. But he might have the different distribution. Let's say one, three, two, three. Possible?
Yes.
Because these are statistics. Energy is being exchanged. You don't know which distribution you will have.
Anything could be it, but total
Anything.
would be 9.
0.0009, it may be possible. Anything. So all distribution are possible. So this is one distribution which is equivalent to A1, A2, A3, and so on. Okay, and there must be up no, let's up to AJ. J we have used. Let's say AN. There are n number of, because here you are saying this is four now four states. So we are saying there are n states, and n can be. Upper limit is capital A. Is it clear?
Yes.
Generally, it should not be capital A. Then essentially all states should have one microstate. Okay.
Yes.
Okay, so this is AJ. Now we know the a priori probability of all distribution are given equal weightage in ensemble average, that you know. What was the a priori probability? That all microstate having the same probability to happen, right?
Yes.
This was a priori probability. All microstates would. So, what will be the probability of having this particular distribution? We are giving a name, not name. It's a symbol that is. This is omega of AJ. Means how many times you will have this distribution. These things I have discussed in last time. Just you remember. Just it maybe feel quite different, but it's not. Let's say here you have how many microstates are there? 9.
Yes.
So if I say what is the probability of having this distribution?
1 upon all the possible distribution.
Not 1 upon. Just remember 9 factorial by 2 factorial, 2 factorial, 1 factorial, 4 factorial.
Yes, yes. This I remember.
Yeah. So this is the probability of having this distribution. Obviously, you said any distribution can possible, but there should be some probability associated with some distribution, right? All distributions should not be equally probable.
Yes.
So this is the probability of that distribution. So what will be that? Now you know that should be a factorial divided by 1 factorial,
1
a2
factorial, A2 factorial,
to n factorial.
A3.
Correct? That's it. So in shorthand notation, what you can write? A factorial divided by, yeah,
Yes.
I think this is the probability of that distribution.
Yes.
Hmm. Now, in this distribution, now we are fixing on this distribution. Distribution we are not changing. No, the probability of having this distribution. Now we have this distribution. Okay. So in this distribution, if I say in this distribution, particularly in this distribution, if I say what is the probability of having energy, having the level AJ, just see. First, we have calculated the probability of having this distribution. Now we know this distribution. Okay, that we have calculated what is the probability of having this particular distribution. So now we have this distribution. After we having this distribution, what is the probability of A1? A1 is 2, right here. Can you understand what I say? Okay, it might be difficult. Just I'm saying again.
Please say once more.
This you can calculate what is the probability of having this distribution.
Yes.
What will be that? 9 factorial divided by 2
By 2
factorial.
factorial, 2 factorial, 1
E-
factorial, 4
Yes,
factorial.
yes, you calculate easily. That is the probability of having this distribution. Now let's say we have this distribution. Then if I say what is the probability of having state 1, P1, then what will be that? Under this distribution, what is P1? 2 by 9. As simple as that.
Yes. Out of 9, there is 2.
If there are two microstates under this distribution means this I have written here, drawn here. Under this distribution, there are only two states in having energy 1. So P1 should be A1 divided by total number of state A. That's it.
Yes.
That's I'm saying. This is not the probability of having distribution. This is under a distribution, under a particular distribution AJ. If you want to find probability of a particular energy state EJ, that is AJ by capital A. So that is probability of having jth energy state in a particular distribution. Is it clear?
Yes.
Now, let's start. Is there any doubt?
This capital A, can I write its summation Aj?
Uh-huh. Obviously. That you can obviously write. Okay. This is under a single distribution, this one. And previously we calculated this is the probability of having the distribution. That should be matter of concern. But in generally we do not concern about this. We think that is the
Can
distribution
you
and
please
hmm?
can you please summarize these two state probability of having this energy state and the whole?
Yes, obviously. So let's say you have 9 microstates. You have to you have make ensemble 9 microstates. That you can make.
Yes.
So you have to make ensemble of 9 microstates. So okay. So you haven't you will take 9 copies of a same macrostate. This is the same macrostate, and you are taking 9 copies of it. And in your copies, you find out that this is the energy distribution.
Yes.
This is yours. Your friend has done the same. In your friend, this is same this macrostate is the same macrostate. Same. He have also he has also take 9 copies. So for both of your A is 9. A is the number of copies. It should not be in real case, it should be tends to infinity, but let's say 9. But your friend distribution is like your friend got it may be greater than 4 as well. But for simplicity, I'm considering like
I
this.
am assuming this and he is assuming this.
Not assuming he's getting this because this is random, na?
Oh,
Energy is exchange.
yes.
So maybe this is one distribution, this is another distribution. You don't know which distribution you will get. That is totally random
Yes.
process. So so his distribution is your distribution is what? 2, 2, 1, 4. How you can write distribution? Distribution is written in terms of AJ. This is okay.
This is 3, 2, 2, 2.
This is I don't know. I've just written randomly. 3, 2, 2, 2. This is another distribution. Two distribution are different. Now there may be many other distribution. You don't know.
Yes.
So what is the probability of having this particular distribution? Probability of having this particular distribution will be 9 factorial
9
divided
factorial by 2 factorial, 2 factorial, 1 factorial, 4
by
factorial,
factorial. Okay? And what is the probability of having this distribution? 9 factorial
9
by
factorial, 3 factorial, 2 factorial, 2 factorial, 2 factorial.
factorial. This is the probability of having this distribution that we calculated. Now let's say you have this distribution. Okay? Now you will calculate in this distribution. Now in this distribution, what is P1? P1 means having energy state T1. That is 2 by 9, correct?
Yes.
What is having P2? That is
2 by
again
9.
2 by 9. P3 is 1 by 9 and
9 by
P4
9
is
is 4 by 9.
4 by 9. Similarly, what is the distribution of having P1 here? 3 by 9.
3 by 9.
Here, 2 by 9,
1 by
2
2
by
by
9.
9, 2 by 9.
That I These probabilities are having of that particular state in that particular distribution, in a single distribution. And this is the probability of having that distribution. Okay, these two things are different. I think now it's clear.
Yes,
Okay. Just it's better. That's why it's always better to think with some example. Okay. So
the first one is under the total thing. It's a possibility of that, and the this one
okay, just
under the my
you
experiment there is.
you under a particular single distribution is maybe under a
Yes,
single distribution. What is the probability of having that eigenvalue? Just take 2 minutes and just digest it. Then I will proceed. Otherwise, just think. 2 minutes. If you have any doubt, you are. It's not difficult. It's maybe a bit confused.
for the language, I am feeling more difficult.
But it's the best way I can explain.
No, for this English language, not this explaining thing.
Uh-huh. So this is the definition. I am writing from even our note. If anybody joins in between, do you have gone through this week lectures?
Yes, but there were some. The language was difficult to think.
What was the main thing he has discussed? What is topic? I did not wait. Because,
There was a he was explaining in the class of the IIT Bombay.
but what was the topic in this week lectures?
This canonical ensemble.
Only canonical and so on, right?
Yes,
Okay. Does he prove the derive these partition functions?
it was in the slide, so there was everything written.
Oh, he was just showing the slides, right?
Yes,
Okay, I see. Okay. Because I saw that he was planning to discuss chemical ensemble. That's why I fixed that I will discuss today chemical ensemble in detail because generally it is not taught in classes in details. Chemical ensemble, how the particle function is. There is a bypass derivation you can say, or as just more trivial derivation is there, but that is not scientific. Scientific, that is scientific, that is not regular, that is quite vague derivation. So that's why I feel that I should discuss this canonical ensemble at least in detail.
is it available in the Macquarie book?
Um, I will share this note. Don't worry.
Okay.
Theory book is very difficult for beginners.
Yes, but I have only that.
Don't be, I will share this. You can buy Talent book. Link I will share. Just buy because that book I did not know about this book in my BSc or MSc because in physics it is well known. In our chemistry, this current book is not that well reviewed, but it's a very, very good book. It's a different, it's a statistical thermodynamics book, or it's thermodynamics and statistical thermodynamics book, not only for statistical, it's for general thermodynamics as well. But it is written in a mathematical language. So it's entirely different book. You can read it. I have not read total book, but some portion I have.
Very much tough.
No, it's not difficultly written. It's writing is not mathematics. It's difficult that you can think, yes, because it's a mathematical approach of looking thermodynamics and statistical thermodynamics. You need not to be
Okay.
understand all things, but you will have a flavor. Just like you have seen already that entropy is the main thing, right? In entire
Yes.
dynamics, statistical thermodynamics, entropy is the main thing. But when we have studied in thermodynamics, entropy just uh, added ad hocly, just dq by t, dq reversible by t, and that is we have, as you seeing that it's a state function, so it's we are giving a name to state function with entropy. But things should not be that. Entropy is the inherent property of the thermodynamics. That is the whole thing. Later you will see from entropy, even also here you have seen in statistical mechanics, Boltzmann gave the formula A is equal to KBL and omega. That is the entropy. That's the universal thing. You from that entropic point of view, you should do the thermodynamics for us. There are 2 point of view is thermodynamics point of view. One is energy point of view. These things are we are all doing energy point of view. But there is another point of view that is entropic point of view. That is more, I will say, more close to the actual mathematical version. Because from mathematics, you can only derive the entropy. And then entropy
Yes.
will have. Okay. So now we can proceed. I
The
think
A
it's
is equal to KB ln omega. Is it valid everywhere in
no.
higher
It's
levels?
for it's for only microcanonical ensemble. For other ensemble, there are different formulas. General formula is rho I ln. There is in for the formula is AB. This is the
Yes.
general.
In the previous class, it was discussed.
This is the Gibbs entropy. And equivalent formula of this is rho ln rho. Same thing. Just in I have written in different.
For
Is this
microcanonical also,
all
in
level?
higher
All
level, is it applicable or not?
for all level. Quantum level. Higher level means you are saying in macroscopic level.
Yes.
No, from this quantum level, you have to derive the macroscopic formula. Now that will do by using ensemble average or some other. Because in macroscopic level, you are not saying the actual entropy, that's the average entropy.
Yes.
That you will calculate by using this ensemble. Okay. So now we can proceed, right? It's clear right now.
Yes.
Okay. So now we are assuming your distribution is AJ. This is your distribution, which is A1, A2, A3, and so on up to AN. Correct?
Yes.
And what was the probability of having your distribution? Let me write it. Probability of having this distribution is, that is A factorial
AJ
divided.
by A fact. Yes. Product over AJ.
Okay, this is
Yes.
when under this distribution, what is the PJ?
AJ by capital A.
Correct. Okay, is it understand? Ah,
Yes.
okay. So now your friend he has another distribution, PJ prime. or Bj, let's say B1, B2 up to Bn. Clear?
Yes.
And here
Bj by capital B.
no, that I am comfortable. It's not changing.
Okay.
So here A was sum over J, and here A is sum over J. But I am not changing. Okay. Now, now understand what is the total number of AJ. Here from this distribution, what is the total number of AJ? Total number of AJ means what is the total number of microstate having energy EJ? Total number of microstate of having energy EJ. What will be that?
Ej by total energy.
Just read it and then guess it. Try to try to answer it. In particular distribution, in this distribution, what is the total number of microstate? Let's say E1. What is the total number of microstate having energy E1? In your picture, what is the total number of microstate with having energy E1?
2.
2. That means E1.
Yes, that is A1.
E1. Now you have this number of copies, right? This is the probability means this is the number of distribution you will get, the number of times. This is the probability, right? So what is the total probability of
Yes.
having this microstate? That is this times AJ.
Yes.
That's it. This is the AJ and this is the probability. That should be the total number of microstudies having energy AJ.
Yes.
That's it. And so it's better to write it. Yeah. Good way it's AJ times this is. So what will be here? Same thing. Just what
Bj
will be?
omega
Yes,
Bj.
correct. This is it clear now?
Yes.
So this now what will be the this is for under this particular distribution, correct? So if you consider all distribution, then you can calculate. Just see, then it will be so total number of microstates of having energy, having energy is 1 minute. Okay, okay. Yes. So what will be that?
AJ into that omega term, total probability.
This is for one distribution, right?
Yes,
This is for another distribution. You are calculating total number of microstate.
yes,
Listen,
then AJ plus BJ total.
in general, you just sum over all distribution. This is for one distribution. For all distribution, you just sum it. Nothing is there. This is
Yes,
total number of microstate having energy is it. Correct?
yes,
Okay. Now, this is okay. But what is okay? This is considering all possible distribution. Don't count. Previous one is for a particular distribution, considering all distribution. Distributions. And what are the total number of distributions? Total number of distribution. You know from here you can have different distribution. Correct?
yes,
Okay. So what probability of having this distribution is this. This is this. There are different kind of distribution. So what are the total
yes,
number of distribution? The sum. Okay.
yes.
Just I'm giving an example, then it will be clear. Let's say there was nine, so it is difficult. So let's say you have four, and energy level can be up to maximum four, you know. Uh, but I am saying there are, let's say, uh, only, I'm saying only two energy levels are there. So then it may be, what will be the distribution? One distribution will be 4 factorial by 1 factorial, 3 factorial. This is one distribution which is 1, 3 distribution. Another distribution may be
4 factorial by 2 factorial, 2 factorial.
2 factorial, 2 factorial. Correct? One is 4 factorial by 3 factorial, 1 factorial. One is 4 factorial
4
by 0
factorial by
factorial,
0
4
factorial,
factorial.
4 factorial.
So these all kind of distribution you can have. Any other distribution you also have like 4 factorial divided by 1 factorial, 1 factorial, 2 factorial, and so on. This is all distribution
If
and
there is
these are,
2 energy level, then these are only possible.
but there may be 3, there may be 4, maximum 4, right?
Yes,
And then that's it. So you can calculate. This is the number of microstate under the probability of having the distribution, right? This is number of distribution with that orientation. You can say. What does it mean? It mean let equals one. What does it mean? This value is four, right?
yes.
So there will have you will have four. Yeah, four microstate or four different. It may be. It means E1, E2, 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 which is one. Another one will be E2, E1, E2, E2, like that, na? So we'll have
4
four
is possible.
four ways are possible for this distribution. Correct? Distribution is fixed. Distribution is 1, 3. This we have discussed.
Yes,
Number of possible orientation under this distribution, like that.
yes,
Now, how we'll calculate the total number of distribution? Just you have to sum all distribution. This is one distribution. And if you sum over all distribution, then it is just total number of distribution. Just one, you see here, what will be total number distribution? This is the all possible distribution, right? 0, 4,
yes.
1, 3, 2, 2, 3, 1, 4, 4. The total number distribution will be this is 1, this is 4, this is 6, this is 4, this is 1. Total distribution is 16.
Yes.
So that will be 6. So total distribution, just I have done this now. So it will be 16 for total number of distribution. That's it. And now here for each distribution, what is, uh, let's pick the E1. Okay. So here E1 is, how many E1 is there? All four are
One.
E1. Oh, sorry, all the, it is 4 0, correct? 4-0. And it is 0. Huh. Here all are in E1. Under
Yes.
this distribution, how many states are in E1? Four states are E1, right?
Yes.
So what will be the number of uh, states with having energy? One, that is 4 under this distribution, correct? Under this distribution 1, under this distribution 2, here 3, and here 0. Okay.
Yes.
So now I'm asking, this thing we have, this is this, this. Just see, this is the code for one particular weapon. You can have total one number of way. Total will be 4. Here you have 4 ways, and for each cases, you will have E1 one time. So total 4 times. Here it will be 12 times, 12 times, 0 times. Just see if it is correct or not. This is, let's say this is
Yes.
particular one distribution. So under this distribution, this is the distribution. This is uh, number of ways of that distribution. In this distribution, how many times you will have E1? 4 times, correct?
Yes.
And this distribution itself occurring one time. So total, how many times E1 is giving? 4 times. That's here you have written AJ times that omega. This omega is here one time and AJ is 4 times. Okay. Here, under this distribution, what is the number of A1? Means having energy E1, that is 1. But this orientation you are having 4 times. Total will be 4.
Yes.
So in that, that's why this is this. So now if you sum over all distribution, then you will have total number of states, microstate with having energy E1. And that will be just sum over this. So it will be 23, 2. And total number of state is 12. Okay. The probability of having energy A1, that is average number of A1, that is 32 is total, and you have the distribution, so that is 16. So it will be just 32 by 16. Average, average is 2. That I am saying. You have to make the average.
Please repeat the last line.
Okay. This is the total number of states you are having with energy E1, considering for all distribution, right? This is
Yes.
clear. And what is the total number of distribution? 16.
Yes.
So on an average, under a particular distribution, how many number of states are there? 2. A1 is there. 2. Here it is 4. Here it is 1. Here it is 2. Here it is 3. So on an average, how it is? How much it is?
This total by 16.
You have 16 ways and total number of E1 is 32. So now if you just take one way, any one, then what will be the probability of having E1?
4 by 16.
4 by 16, right?
This particular first one, it has 4 possibility and total number is 16 total possibility.
possibility, these 16 are possibility of having these orientations.
Yes.
So this is not related with this anyway. Just let me repeat it. Just let me draw it. Otherwise, you will not understand. Okay. So one possibility, you have four microstates, right? Four copies. Let's say. Now, under four copies, you have distribution. I'm restricting to two. So one distribution may be 4, 0. There are two energy levels, E1 and E2. This is clear?
Yes.
One is 4, 0. Under this 4, 0 distribution, under this 4, 0 distribution, how many number of ways you will have? Under this particular, uh, not distribution, let's say I'm giving a name, under this particular orientation, no, 4, 0 orientation, 4, 0 orientation, how many distributions are there? How many distributions are there? 4. How we can calculate
Yes.
it? 4 factorial divided by 4 factorial, 0 factorial. So it is 1, not 4. It means it is just E1, 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 E1. Any other is not possible.
Yes. This one only.
This is under this 4, 0 orientation. Is it clear?
Yes.
Okay. So now under this orientation there is 1. But each orientation, each distribution, this is one distribution. Under this distribution, how many numbers you are getting E1? What is P1? What is the sorry, what is A1? Number of having E1. What is
4,
4? What is A2?
0.
0. This is one orientation. Okay. Good. There may be another orientation possible. That is, let's say 3, 1. So under this 3, 1 orientation, how many distribution you will have? How many ways you can have this distribution? That is 4 factorial by 3 factorial, 1 factorial. So it is 4. Correct?
Yes.
So it is E1, 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 E2. It may be E1, 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 E2. It may be E1, 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 E2, and it may be E1. These four orientation is same, but you are having four different ways. Correct?
Yes.
These things, this orientation we have mentioned as omega aj. Not this is actually aj, this orientation. And this is actually omega aj means number of times you are having this orientation, number of ways you are having this orientation. This is omega aj. One, here omega aj is 4.
The third one is same as the first one.
Yeah, okay,
Yes.
this 4. Now, what now under this 4, 4 distribution, what in first one, what is the A1?
3.
For all cases, A1 is 3, A2 is 1, correct?
Yes.
Now, what else possible? one more. We can do any other, right? So it is, let's say, and 2, 2. So 2, 2, what is the probability? Okay, no, what is the
4
number of
factorial by 2 factorial, 2 factorial.
6? So we'll have 6 distribution. So it is E1, E1, E2, E2, E1, E1, E2, E2, and all 6 we will have, correct?
Yes.
For all cases, A1 is 2, A2 is 2.
Yes.
This one, okay. One more, it will be 1, 3. Here also you will have 4 factorial by 1 factorial, 3
1
factorial,
factorial, 3 factorial.
4. So these 4
Yes.
are E1, E2, E2, E2. E1, E2, E2, E2. E1, E2, 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 and one more. Uh, these 4. Now here, what is A1? 1. A2 is 3. Correct? Is it okay? Hello?
Screen was gone.
So now it's visible?
Yes.
Okay, so is it okay?
Yes. A1 equal to 3 and A2 equal to 3. Sorry, A1 1 and A2 equal to 3.
One more is possible, that is 0, 4. Number of
Only
ways,
one is possible.
1 is possible.
A1 is 0, A2 is 4.
Now we can have resemblance. These things are distribution, and this is the number of ways of having this distribution. And under a particular distribution, these are the this is the number of microstate with having energy E1. This is the number of microstate with having energy A2. From here, you can calculate the P1, which is 4 by 4. P2 is 0 by 4. These things we clear.
Yes.
This is under a particular single distribution. Now, from single distribution, now we will go to the total distribution. Now what will be the number of total distribution? First, you say what is the number of total distribution? Under this orientation, what is the number of distribution? 1. Under this distribution, what is the orientation number of distribution? 4. There are 6. There are 4. There are 1. So, what is the total number of distribution you are having?
16.
16. You are essentially, you can see 16 distribution I have drawn. So this is the total number of distribution. So 4 copies you are having, correct?
Yes.
Now, what is the total number of state with having energy E1? That means A1, correct? From this distribution, just understand, from this distribution, it is 4.
Yes.
From this orientation, correct? From this orientation,
Yes.
what is A1?
3 into 4.
3 into 4, because for this orientation, you will have 4 distribution,
4
and this
microstats possible.
distribution, yes, for each distribution, it is 3. So total number of state will be 3 into 4. So
12.
here it will be 6 into 2. Here it will be 4 into 1, 1 into 0. That I am saying. So total number of state will be 16. That is this 4, 4, 12, 12, 0. Correct?
But the probability is becoming 2.
Now you understand what is the now you just summarize. What is the number of distribution? 32.
Yes.
This is 32. Now what is the number of now you randomly picked up. If I say what is the randomly pick and say the what is the number of A1, what we will say? You have to average, na, what is the total number of A1? 16. And total number of distribution is 32. So it will be 2 now for each just for one distribution it is 2. That's it. Here it is 4. Here it is 3, 3, 3, 3. Here it is 2, 2, 2, 2, 2, 2. Something like that.
So the average is 2.
Average is 2. That's I'm doing here. So this is the total, and the total number of this is AJ times rho j, and you summed it means 16. Like for each distribution, this is AJ times rho j. You are having EJ. This is AJ times rho j. Correct? Now, when you summed over
Yes.
it, that is the total number of microstate with having energy EJ, and this is the total number of microstates actually, total number of distributions. So just you divide it, and you will have the average. That's the thing. Okay. So the average number of microstates with having energy EJ considering all distribution. That is sum over AJ. This is how just age, sorry, not sum, average over AJ. So it will be AJ times omega AJ, this sum over this, and divided by total number of distribution. Got it?
Yes.
Okay. Now this is I have done for AJ. You can done for PJ as well. What will be PJ? So if it is AJ, it's clear.
Instead of AJ, it will be
You can do their PJ, or it's better to do just AJ times capital A.
by capital A.
Huh. Capital A is not changing.
Yes.
That is that is always capital A 4. So it is just 2 by 4. It will be here. It means up. So it is just AJ. So you can write it as in general. You can write it 1 by A sum over J AJ times rho J DJ. This okay.
Yes.
Now you know this is what is this? Considering all distribution, this is probability of previously we calculated for under a single distribution PJ was AJ by capital A, correct? This is for under a single
Yes.
distribution. It is probability of having a microstate with energy EJ considering all distribution. Okay.
Yes.
Now, if you know PJ, then for any property, any x average, any property of that state, you can calculate, which is sum over j, xj, pj. That you know.
Yes.
That's it. This is our technique. And pj is not infinite. Both aj and a, these both are high. Here I have taken 4. If it is infinity, then aj will also be very high, but pj will be finite. Maybe 10 to the power 23, 10 to the power 22. So it's 1 by 10. Both are infinite, but it is okay. So now you can calculate the average values from canonical ensemble. Is it clear?
Yes.
No. Just digest it and then we'll proceed. I'm writing. So what is the Ultimately, we have AJ. Some of our J is already there, so it's not better to write like AJ, it's AJ, and then it is omega AJ, this one, and here it is A over J omega H. Correct? Just I put PJ. So it is very difficult to calculate, correct? Because you have to consider all distribution. This is all distribution. Sum over J is there.
Yes.
It is very difficult to calculate. So how you can calculate it? That we'll see. I don't think today it will be covered totally, but okay. Just see it if there is any doubt and fine. 1 minute.
Please explain the X average part,
I'm fine.
the last three lines.
Okay. What is the problem?
The last three lines.
Three lines.
Sorry, two lines.
Oh, XJP, this you know, right?
Yes, that I know. The last line.
The put this PJ.
The term that is in the denominator, what is it?
This one, na?
Yes.
This one. Where is the problem?
Okay, that is xj into the probability of j, pj.
Hmm.
Okay, no, no, it's okay.
Better to write it like this.
I have written wrong thing.
That's correct.
Yes.
But my concern is to calculate this, you have to deal with all possible distributions so that you can calculate this PJ. So PJ calculate करना ही मुश्किल है.
Yes.
So now what will you do? What will you do? Just rewind here for this distribution. What was the omegas? For this orientation, there were, if you remember, there were four copies, correct?
Yes.
And the orientation were 40, 31, sorry, 22,
2 2. 1, 3, and 0, 4.
What was the probabilities of this orientation? Not probabilities, number of ways of this orientation. That was, this
4
is
factorial by 4 factorial into 0 factorial.
like this, right? I'm saying it is 1, and it was 1, right?
One.
This is total number of ways was 32, sum over all.
16.
52, no, 16. 52 is was 16. Okay, is correct.
Yes.
Now if I plot, it's, this is this, and this is the T. This is A1, this is A2, like that. Okay. So here are 5 values: 1, 2, 3, 4, 5. For 1, omega 1 is 1. For 2, omega 1 is 4. 3, it is 6. 4, it is 4. Again 1. Okay.
Yes.
So if you plot it, it will be like this. Any doubt?
No.
This is for 4 copies. If you increase the number of copies, you can try with 6. But in general, if there is, it should be infinite number of copies. It should be
The graph will also be same.
no. The graph, if you can see, it is a property of nature. If there is a huge number of distribution, then this graph will be, this is omega and this is A, it is Aj, and this is omega Aj. This graph will be like this.
It will have maximum at the center.
Not center at a particular value. You don't know which value. This is called delta function like graph. Delta function, you know?
Yes, it was discussed in previous class.
So it is direct delta function. You can calculate with 6 copies. You will see it will narrow down. How many? If you increase the number of copies, it will be narrowing down, narrowing down. When it is infinite, it's just a delta function. So you will have basically, you can write, there will be a most probable distribution. This is called. This is not only true for this case. In nature, all cases when there is distribution and huge number of possibilities there, nature will automatically select most probable possibility. Let's say I'm making with a star. This is most probable distribution. Delta function means this is the number of ways of having any other distribution is essentially tends to 0, and for having a distribution Aj star, this is actually huge compared to this is infinite. This is the definition of delta function. You get it?
Yes.
So it essentially signifies the negligible, right? So if you summed it, all distribution, that is also negligible compared to that most probable distribution. Because you are summing over all these points, but this is infinity, right?
Yes.
So you can write it. So in general, you can write this. So summed over means you can take this, right? When you are taking the sum, you are taking all distribution, but only the most probable distribution has the Infinite contribution in other are tends to zero compared to this. Means it may be, let's say, 10 to the power 22. These are 10,000, 10 to the power 2,
Yes.
something. Then what will be, just you can take this. These are negligible compared to this. You get it?
The yes, it is huge than the others.
Alright, so that's why we will deal with the most probable distribution. Now you guess it. What is the most probable distribution? What should be the most probable distribution?
Where all level has equal number of molecules.
Number of microstate, not molecule. These are microstate.
Yes, micros.
Here it is 2, 2. That's the case. So most probable distribution is where all levels, this A1, A2, A3 star, these all levels are equally filled. A1 star equals to A2 equals to A3. This should be the most probable. More or less equal. Because when this is huge, 10 to the power 23, then it should not be exact equal, but more or less equal. Correct?
Yes.
This should be. So now you can neglect all other distribution. We will just focus on the most probable distribution. This is this. This is the most probable distribution. And you can calculate this, the number of ways of most probable distribution, that is a factorial by, correct?
Yes.
And you know this A is sum over J of AJ star. This is true for all distributions. So it might not be AJ star, but for AJ star also it's true. And the total energy is also constant. That is not changing. That is AJ star, EJ star. These things we have already done.
Yes.
So now it's easy. Now what was our, so PJ? You have calculated PJ. PJ was, just I'm
EJ
talking about
by
these things, was our PJ. This was our PJ. Correct?
yes.
So just write it. It is our PJ. But we will now only choose the most probable one, so we can drop the summation. This should be AJ, not EJ. Okay. I have written here. Typo. Distribution are written in terms of AJ, not in terms of each. Each. Okay.
Yes.
So just I am taking the most probable distribution, not the all distribution. So now it's clear. Now you can calculate the xj easily. So what will be xj? Sum over j, then xj, aj star, this one, and, or better you can write it like this, otherwise it will be again confusing. Later we'll see. We have it like this. Okay, start.
Yes.
These you can calculate. Now you have don't need to consider all distribution. You have to just consider most probable distribution, and you have enough knowledge about most probable distribution where the all states are equally filled. That is the most probable distribution.
Yes.
So now using this we can calculate the particle function. So should we do this today, or just we have to
What?
calculate, just we have to calculate this xj? Means we xj is different. If it is energy, then it is ej. If it is enthalpy, then hj. If it is entropy, then sj, something like that. It may be anything,
Yes.
but we need to just calculate pj. That is invariant. So we have to calculate the Pj only.
Yes.
So I'm saying, should I calculate today? Oh, we have not. Oh, one thing. So J is not needed. Just you see. Oh, means I'm saying
Yes.
here.
This is a particular.
No, no. Here no J was there eventually. Why J is there? J already this notation. Here no J is there. J is all written in the distribution. You see, not omega J. I was omega is function of H. That was the type. Okay. दो बार J लगाने का कोई मतलब नहीं है ना, ये तो already J इधर लिखा हुआ है. That's it. So
Yes.
now we have to calculate these things, this Pj. Pj we have to calculate it, this probability of. So what will be that probability of? That is clearly from here what you can write. AJ star by a capital A. It should be na, because it's a single distribution
Yes.
right now. It's not the all total. For single distribution is the formula. It cancel na. So it's a formula you have no, but it is we have to take only most probable one. So it is AJ star by A. Correct?
Yes.
So just you write it. So
Yes.
this is
XJ is.
our XJ. Means we are taking only the first we studied for all distribution, but later we find out among all possible distribution, one distribution is hugely dominating, and that is the most probable distribution, and we are now talking about only that. So this is our
We are taking the average with respect to the most probable.
most, because we are taking all distribution, but all distribution are negligible compared to the most probable distribution. So we are
Yes.
considering only the most probable distribution. So see, that means in this case we are talking about only this. If you do it, then what will be the P1 or A1? 2. And after doing 16
Yes.
by 32, what we will have? 2.
Two.
So it's correct. It's matching, right? If you only choose this one, then also it is 2. Get it?
Yes.
So for only 4 copies, it's matching. Huge number of copies is obvious actually. So there is
Yes.
nothing wrong. So now by using this formula, you can calculate. But you have to keep in mind there are two constants. These are two constants. This you have to always keep in mind that overall number of uh, a copy should be fixed. That I'm not changing. We have take the example. That's it. So if this is A is not changing, this should not also be changed over total number of epsilon, because it is in a contact of thermal bath. Overall energy because it's equilibrium. So overall no energy is coming. Energy is coming exchanging within the system. So total energy should not be changed. Correct.
Yes.
One system is giving, another system is losing. That's okay. But total system is not changing energy. So in that way, it's that. So now our next task is we have to calculate this Pj. If I calculate Pj, then automatically Xj we can calculate. Okay. So today I think it's not possible because it will take some time. So essentially we will see later that Pj will be e to the power minus beta Ej divided by sum over. Oh, that just see what we actually calculate. We have to calculate Pj, correct? Have to calculate.
Yes.
That is this. So that means AJ star divided by sum over AJ star.
Yes.
That we need to calculate. So better you have to, it's better to write it like this. Xj is sum over sum over j sum over j xj AJ star divided by sum over j AJ star.
AJ.
AJ star. Or this is true for any AJ.
Why this is AJ star?
Because for AJ star also sum over AJ star is A.
Yes.
For most probable distribution, it's also true, na? So we can write it.
Yes, but if I write this is only AJ, then will it be wrong?
No, this is true for any distribution. It should not be the most probable one, but it's true for
But
most
the above
probable
part
one
I
also.
have to write AJ star.
And then because now we're dealing with only the most probable one. We are not bother of other distribution.
Yes,
That's the reason. Now we have to just calculate this age star. What is this age star? And you will find out later. We'll do it. Age star will be e to the power minus beta ij.
yes,
Just put it. That is our canonical ensemble. Nothing. And this is called the partition function actually. Okay, that we'll do next class because it will take some time. And after having this formula, we can calculate any property. Then we'll calculate all properties. This part up this derivation we have not done before, but after having the canonic partition function, rest of the part we have done, calculating the various properties. Correct? So that thing we will do again.
yes,
We'll calculate the various properties for the canonical ensemble. This canonical ensemble should be studied in detail. Later, if time permits, then grand canonical one also be we can done. But for grand canonical one, you can see here only the energy is changing. There the n will also be changed. So distribution will be again one more distribution we will have in terms of n as well. It will be more complicated in that case. Here you are having distribution in terms of only energy, right?
yes,
E1, E2, E3, EJ. But there for n in terms of n also you will have energy n1, n2, n3, nj. So two that ultimately you will have two factors there. Then okay, it's okay, but if I don't know what is in the syllabus, what is he is teaching. So I will look at if then canonical he taught, then obviously I will do it. But now in next class also I will focusing on the canonical because canonical, if you understand canonical, you can do grand canonical. That is not a big deal. But first you have to understand that. So I think this canonical part is clear, right?
yes,
It is not difficult, it is confusing. You have to just think it. For simplicity you will have to take some example, then you can do it. Just I have taken that 4 copies example, right, or 9 copies example, then it is easier to understand.
yes,
Otherwise you can't get it. So always in statistical mechanics or any statistical things you should consider a smaller sample space and you have to just think whether it's correct or not. That you can do. So just gone through it because now you can understand it. You have studied previous courses as well. Now in this derivation is not very difficult, but I will suggest that please revise. It's not very huge. Just see 5 to 6 page. Just understand it how it is happening. It might be some point it is confusing, but it's okay. You can do that. Then in next class we'll calculate it. Calculate the partition function and the various properties. For that, we need some mathematical tricks, Lagrangian multiplier we need. So that means we have to calculate AJ, correct? AJ star we have
yes.
to, AJ star means the most probable distribution. So there is a
Most probable.
prescribed technique to find out most probable distribution that we will follow. What is that? You can guess it. How you can find most probable distribution? Most probable thing. What is the
Where first derivative is zero.
exactly? That's it. We have to make the first derivative is zero. That we will do that in the next class. But we have to keep in mind, we have to keep this constant. Just while doing first derivative zero, you can't violate these two conditions. So for that, we need
Yes,
to incorporate the Lagrangian multiplier. Then we can calculate the age star. That's the only thing. After calculating the star, it's clear. Okay, I think for today it's enough. Yes. Okay, so let me first stop screen sharing. We have one device. Okay, okay, okay. So I will share this note, and also this note from where I am doing this all stuff that I have, but I'm not sharing right now because then it will be very horrible to you or other. So that's why after this course I will share it. Okay,
Sorry, today I consume much time for this.
much time for this means. Okay,
To
no,
understanding these
it
things,
very
I consume
no
much
no no
time.
no no no. It very important to understand this. This is the basic of statistical thermodynamics. If you don't understand canonical ensemble, the rest of the things is nothing. You can't proceed. So it's good actually. So there is no problem. In next class, we will do the rest of the canonical ensemble. Canonical ensemble will do more next class and after that class as well. It's too huge. You have to cover all canonical ensemble. Then we'll see what is in the course going on. Then I will go accordingly. If Grand Canonical is going on, then I'll study that. I'll discuss about some Grand Canonical things. And later, I think probably Ising model, Boltzmann kinetic equation, these things has also been discussed. So these things we will also cover. I don't know. I have to go through. In this week, I was planned to do this. That's why I'm not going through the lecture. So next week, I will go through this thing. But you gone through this today's note, and if you have any doubt regarding this, you should ask in S class or other it's better to ask in S class because then I will record it. Otherwise, you can ask me in WhatsApp also. That's not big, but you should go through this. Okay, do it by hand.
Okay,
It's 4 to 5 page. Do it by hand. If you do it
okay,
by hand, then it will be very clear to you. Okay, so okay for today
okay.
it's okay. Thank you for joining. Again, we'll meet in the next class.
Thank
Next
you.
class is 17. Okay.